break the countertop of your kitchen, you will see that that's going to fail in very brittle manner. So if you do have reactivation now in this brittle rock, very likely here in this case, now you may create a big wave that goes all the way to the top. And this is going to be a function of how the rock fails. So as a summary, the rock can fail in brittle or ductile manner, but it depends on the type of rock and also depends on the confining stress. As you go deeper, the rocks tend to be more ductile. Some rocks, like for example igneous rocks, you can get very deep and they may be still brittle. But sedimentary rocks, mud rocks, you get very deep and they get more and more ductile. Okay, so at this point we have covered mostly all the concepts that we need in order to solve real life problems and real applications. And this is an example, but if you come back to the first day of class and we talked about the things that we would do, we talked about faults, like, where is it? Like this one that we just talked a little bit before. We talked about natural fractures, reactivation of natural fractures, and that's what we're going to see right now. What are the stresses that make faults reactivate, and what are the stresses that make natural fractures also reactivate? That reactivation of natural fracture is very important for increasing permeability in unconventionals. We also talked about deformation. Now probably you can understand a little bit better why some geological formations they bend slowly, and that will also be a sort of a ductile deformation because they bend with time. They do not fail. That will be a ductile deformation, but sometimes you may have faults that will be the equivalent of a brittle deformation, a very localized failure. It's the same phenomenon, but at another scale. We also talk about salt dumps, if you remember. And something that we said is that this type of failure is a viscoelastic failure. The rocks, they creep and they fail very slowly with time. And we have also seen what are the mechanisms that are going to help us to understand wellbore stability. In wellbore stability, we're going to see tensile failure and also shear failure. And we already have the equations in order to solve that. So the first example and the first category of problems that we're going to see are the reactivation of faults and calculating stresses on fractures, because that's very important for several applications. And also for understanding structural geology, why we have faults in the subsurface and what is the orientation of those faults, and if they could continue moving or not. All right, so let's go there. So okay, so we're done with this. Now I'm going to talk about faults. And in general, there's going to be faults and fractures, and mostly when I talk about fractures, it's about shear fractures. And related to this, we want to calculate stresses on a plane. Many times that plane is going to be our fracture. So can anyone tell me why faults form and what type of failure faults are? And while you think about that, or while you speak, I'm going to draw here a schematic. Any idea?
From tectonic movements.
Okay, so what do tectonic movements, what is the implication of tectonic movement?
Cross faults.
But why? Yeah, I would say mostly compressive forces, at least the tectonic plates. So here, what I'm trying to do is, so this is a surface, and sometimes if we have a sedimentary basin, and as you said, if we have tectonic plates that are driving the movement and are adding compression to these layers, probably at a long time ago, and let's see how this drawing comes up. It looks like a bird. I wanted to do a dinosaur, okay, but okay, so a long time ago, you may have had a very recent sedimentary basin, very sharp mountains, but after a long time and you have a tectonic plate movement, the same sedimentary basin now, it may fail in shear, and that failure in shear at a very large scale is going to be what we call a fault. Are you guys familiar with the term what is a rock joint? Can anyone tell me what a rock joint is? Anyone? No? Wait a minute. I think that I did a mistake over here. What did you say, Mr. Eldawe? It's a rock joint is a type of fracture, but it's mostly a type of fracture in which there is no relative displacement of the faces of the rock respect to each other. Many times a rock joint, as if you go to an outcrop, if you see a fracture in the rock, they are caused by when the rock is it's what is called exhumated, or it comes from a deep depth. Temperature is going to go down, the rock is going to cool off, stresses are going to go down, and that makes the rock break. But the rock will break in tension most times. It's not going to break in shear. We call a fault a type of shear fracture in which there is relative displacement of one face of the rock to the other. You see, that point originally was in contact with this one, but now this one has moved up and this one moved down. And this is a type of a shear failure. So, after a long time, now we may have a longhorn here instead of a dinosaur. So faults, they may take a very long time to form, okay? So this is rock failure in a long scale and also in a long time. But it's rock failure, and we can use the same things that we have learned in order to understand these faults. So probably after a long time also, you have some erosion in here. Now, your mountains probably are not as pointy as they were before, and probably here you have a river, I don't know, something like that. But what you should remember is that faults is just rock failure, but at a very large scale. And we're going to use the same concepts that we have used before in order to understand when faults form and what is the orientation of faults. Look at this example one more time, where we have a fault that was caused by tectonic strains. This type of failure is exactly the same of the type of failure that you will have in the laboratory if you were to load a rock sample in horizontal direction, and you will expect a fracture which is very steep with respect to that plane, right? So if I were to move this like that, this is the same thing that you have been seeing in the laboratory. It's a shear failure, and its angle, can you tell me what that angle is going to be? Plus, you remember that? The friction angle divided by 2. Is exactly the same thing, but now it's in another direction. Okay, so let's try to understand now how we can have different types of faults and different types of orientations according to the stress, in situ stress. Before we do that, probably it would be a good idea to revisit some conventions about the orientation of faults. So, for example, if I said that in this place the north is pointing to the mountains, the east is pointing in this direction, and then the depth is going down, and if I assume, say, looking from the top, now I get into a drone and I look at this fault, and from the top it looks like this. I'm going to call the strike of the fault the intersection of the fault with the horizontal plane. So if the surface is horizontal, then let me change this a little bit to make it a little bit easier to see. Let's say that the plane is actually, it's at an angle, okay? That's the angle of the fault. And this is when I look from the top. I'm going to say that the strike of the fault, or the strike angle, is going to be the angle between the north and the intersection of the fault with the horizontal plane. And how steep that plane is in its steepest direction, that angle is going to be called dip. Let me go to a 3D example to exemplify this a little bit better, okay? But there are two things that we're interested in mapping faults and fractures. And they are defined by the strike and by the dip. Let me continue over here. And let me check my notes just to make sure that I have the right drawing. Instead of having now a top view or a horizontal view, let's draw what is called a block diagram, in which now we have a fault which is cutting through some sedimentary layers. So these are the sedimentary layers. Do not draw this with ink yet if you're writing with ink, because I'm going to cut this cake. Okay, I'm going to cut it with an angle which is this one. So that's the plane that we're looking at. And again, on that plane, I can define. Let me bring back my coordinate system. The strike, and now you can see more clearly, is going to be the angle between the north and a line which is intersection between the plane and a horizontal plane. Actually, that line itself is called strike. Okay, and the strike angle is going to be that angle between the north and that line. And if I were to draw here a line which is a horizontal line, and this is the line of maximum slope but this doesn't look very horizontal. Let me draw it again. If I were to draw the line of maximum slope in that plane, that angle is going to be the dip angle. So how do I know which is the point of maximum slope? Well, that's going to be a line which is perpendicular to that line. And you can also think of that line as if you were to drop a drop of water somewhere over here, the water will go down. It's not going to go to the sides, right? It's going to go down through the line of maximum slope. That line and this line, which is in a horizontal plane, that's going to define the dip. So the dip is the maximum angle that you can measure between a horizontal plane and the plane that you are dealing with. For the strike, we're going to use two conventions. One is called the Quadrant Convention. And for example, in that one, we will say that strike is going to be equal to, what do you think this angle is, more or less, eyeballing? Let's say 30, okay? So we'll say the strike of this fault is from the north 30 degrees towards the east, okay? Or you could also say, if you were, for example, looking in the other direction, if you wanted to measure this angle, you could say this is equal to from the south 30 degrees to the west. It's the same thing. This is very useful when you go to the field, because when you go to the field, say if I want to measure the strike of this whiteboard, right, and I'm looking to the north over there, I'm going to say, okay, I look at my compass and I say that this is 35 degrees from the north towards the east. So it's much easier to work with this in the field. The other convention that we have is called the Azimuth Convention, and this one is much easier to use when you are doing computations. And in this case, we'll say that the strike of this fault is 0.30. And that's an angle which is measured clockwise from the north, and also you put 3 digits. Okay? We're going to see later on that the strike also depends on the dip also depends on the strike. So if I have a plane that is dipping in this direction, that's the north, I'm going to say the strike is 30 degrees. However, if I have a dip, let's say, going in this direction, like this, and that's the north, I'm not going to go this way. I'm going to go always clockwise. So I would say the angle of this is going to be, say, 150 degrees from the north. So it's this angle over here, because it's dipping in that direction, and so on. Okay? All right. So we know now what is the strike angle. And the other parameter that we need to define is the dip. And the dip is just going to be an angle which is between 0 and 90 degrees. So 0 means a horizontal plane. 90 degrees means a vertical plane. And you just can write this, for example, to me, this one looks like, say, 50 degrees. And if we could add more information, and we could say this angle dips 50 degrees towards the, apparently is closer to going to towards the east, or towards the east-south. Can you see that? So when I say dips towards the east, that means that, let me move this down. Oh. It would mean that it's going in that direction. So if that's the north and this is the actual plane, this one, no, wait, if the north is, this one would be like that, right? So if that's the north, this is the strike, this is the angle, it dips towards the south and towards the east. But the most important thing is going to be the angle. Once we know the angle of the dip and we know the strike, we need everything we know about faults and fractures. Okay, so now we know how to map this. We know what are the variables that control the geometry of faults. But how do you actually map faults? Anyone knows how to do this? What kind of tools would you use to detect and measure fractures and geometry in the subsurface? One is seismic. Very well. So if you have seismic data, you can and especially if you have 3D seismic, you can interpret that those images and interpret what is the orientation of faults. Usually, as you can see, you have already interpreted faults in this direction. What do you think the dip of those faults is? It's kind of difficult to say, okay? Pay attention that always in seismic, the horizontal scale is not the same as the vertical scale. So remember that. If you want to calculate the dip, you will have to do the arc tangent of this divided by that. and that will give you the depth of the fault. And in this case, we have a 2D volume, but if you had a 3D seismic, you could also see what is the deep, what is the strike of those faults. So that is one method. Mostly structural geologists and people that work with seismic data, they know how to do that, but you should also know, how to recognize faults in this type of seismic data, because faults are very important for reservoir engineering. Are you guys going to the lunch tomorrow with the external advisory committee? You should, okay? Those guys are very nice, and it's very good for doing networking. One day, one member of the advisory committee told me that they wish we had more seismic in our course. And I'm working on that. So in the homework, I added a little bit of seismic, and I plan to add a little bit more, because this is what we deal with. The geomechanics is going to be based on these models. It's not going to be the nice boxes or tiramisu cakes that I draw in paper. It's going to be something real what you have to deal with. And that requires geological interpretation. Okay, so seismic. You can interpret faults from seismic. What is another method that you can use to interpret and measure strike and dip from in the subsurface? We can't see, right? If we're trying to see faults 5 kilometers in the subsurface, we can't observe those. We need some other methods. So one is seismic. The other one is going to be Wellbore Imaging, okay? So I have written that in here, but it's just you image the wellbore. If you took, I'm not sure if Professor Torres Verdin goes through Wellbore Imaging. He does? Yeah. So you can take an image of the wellbore by measuring electrical resistivity at the face of the wellbore, or by measuring also the time lag of sending a wave around the wellbore. If you do that, you will obtain an image of the wellbore which is very similar to, I didn't get to that part yet, but let me see where I can find that. What time is it, guys? Am I getting close to 12:05? Okay, I think I'm getting close to the end, but I'm sure that I'm going to find something quickly, but just type in this. So I'm working on the chapter about faults. I hope to have it ready by next week, okay? So this is not the best one, but here I'm interested about locating fractures. Okay, so that looks as a good one. Okay, there was a better one somewhere over here. That one, okay? So you can take image of wellbores and you will see that these sinusoids, when you wrap all the image, they corresponds to planes. If you know what is the position of the top of the sinusoid respect to the north, so this is angle from the north, 0, 360, what do you think is going to be the strike of this fault, of this fracture? So the top is kind of going 30 degrees from the north, right? There is the north. This is the top. That's the top of the ellipse. So it's a plane something like this, right? And the strike is going to be this line. So probably 150 degrees, 140 degrees from the north. I'm going to show you some images later next week about this. But with Wellbore images, you can also do the same. The strike is going to depend on where these two peaks are, that one and this one somewhere over there, or what this is going to be the bottom, and that's going to be the top. And the dip is going to be proportional to the amplitude. So imagine that you have a horizontal plane. This one will show up just as a line in this direction. If you had a very steep fracture, the amplitude will be much bigger. So the amplitude and the position of that sinusoid is going to allow us to calculate what is the strike and dip of faults in wellbores. And this is very useful because usually with seismic, you just can map big faults. And with Wellbore imaging, you can map big faults too, but also you can map small fractures. So you have two levels of resolution in which you can do. And furthermore, if you're drilling a wellbore and you're drilling into a fractured rock formation, and let's say there are some fractures across this wellbore, you could from here map where all those fractures are. So you will have a map of the fractures as a function of the measured depth of the wellbore. You will know exactly where all of those fractures are. So I'd like to, in these 5 minutes that we have left, I'd like to talk about one more thing. You can see that it's a little bit difficult to draw in a paper strike and dip of faults because it has to be a three-dimensional plot. And even in this plot, you know, I'm just drawing just the dip. You don't know what the strike of these fractures are. So in order to deal with that problem, and in order to map not one fracture, but to map thousands of fractures, we use something which are called stereonets. In those stereonets, what we use is what is called a lower hemispherical projection, in which I'm going to try to draw